Okay, on to P4 waves, and we're going to look at longitudinal transverse waves. On the top here I'm just going to explain the difference between them. So longitudinal and transverse. What you need to know, well, I'd like you to just learn V, P, D, O, E, T, and that'll explain everything. So in a longitudinal wave, in both of these waves, energy is going that way. In a longitudinal wave, it is parallel to. So the vibration is parallel to, and I just remember it, there's loads of L's, and that begins with L. Then there's transverse, well, that makes a right angle, and that is the vibration is perpendicular to. So ultimately, a longitudinal wave, the vibration is parallel to the direction of energy transfer. A way to think of it is in a slinky, you'll end up with places where it's compressed, places where it's stretched apart, places with it compressed, and that's because you're sending energy that way and vibrating it backwards and forwards. If you were to then take it and move it up and down, you'll end up with your slinky making waves. Now both are moving energy. Okay, now you need to know that longitudinal waves are, let's change the color, sound and pressure waves, and transverse waves are light and water. So with that little bit in terms of the summary of the types of waves, we should be able to now answer this question here. So it says, what is a transverse wave? Again, if I was on my exam, I'd write out, whoops, V, P, D, O, E, T. Transverse wave, okay, get it. The energy's got to go one way, so it's the vibration is perpendicular to the direction of energy transfer. And the question says state two examples, light and water waves. There we go. Now the next part now is we've got a boat using sonar to find the depth of the ocean floor. So how sonar works is, imagine there's the sea, there's the floor. We're going to send a sound wave, and this last part is around ranging, so you can use it to find distance. So imagine I've got a little bit of a boat on there. It's going to send out a sound wave. That's going to reflect off the surface and go back. And the great thing is, scientists know the speed of sound in water, or whatever medium, we've measured it for everything. Imagine someone on the boat, they're going to have a stop clock and they're going to time it. And if we know the speed and we're going to collect the time, we can then use that to collect the distance to the floor. So imagine you've got a submarine, it's going to be echolocating to make sure it don't bang into the sea floor, because that'd be pretty bad for everyone on the boat. So here we go. It says it's going to take 1,200 milliseconds. So divide by 1,000, that's 1.2 seconds. And the speed of sonar in water is 1,500 meters. What's the depth? Now the crucial part is, we know we're going to have to work out, speed, but because the sound has to go there and back, we need two lots of the distance. So now I can rearrange this for the depth. So D equals S times T divided by 2, because 2D would be speed times time, but we only want one lot of the distance. So that's going to equal 1,500 times the time, which is 1.2 seconds, divided by 2. And I'll just shove that in the calculator now. And it should give me an answer. 1,500 times 1.2 divided by 2. And we've just worked out that the depth equals 900 meters. So in essence, how does this work? We know the speed of sound. We're going to measure the time, and then we're going to use speed equals two lots of the distance divided by the time to help us work anything out. So that's that in terms of types of waves and how to use echolocation.